the instructors and advisors here at FSI this summer, and our first presentation is going to be two of my advisees. This is Reece Moellenhoff and Samyuktha Senthilkumar, and so they're going to be talking to us a little bit about using fluorescence spectroscopy to detect six-diol purine.
All right, so our project is using fluorescence spectroscopy to detect six-diol purine, and I'm Samyuktha Senthilkumar.
And I'm Reece Moellenhoff, as Sean Hoskins said. So what is six-diol purine? Does anyone know? Like anything?
Josh.
Anyone know anything about chemotherapy then? Maybe? Okay. So six-diol purine is an anti-cancer drug, most commonly used for acute lymphoblastic leukemia, which is most commonly found in children, and it originates in the bone marrow. And it's also used for anti-inflammatory diseases such as inflammatory bowel disease, and it is also used for decreasing the chance of rejection in the transplant of solid organs. And so within the body, in the intestine, it turns into 6-diol-guanine, 6-TG, which is used within the DNA as a nucleotide. It replicates guanine, which is one of the four nucleotides. And because of this, it disables the cell and it reprograms the entire cell. And the body thinks that it looks like a normal cell, but it is not doing anything that a normal cell usually does. And so some side effects of this are jaundice, which can lead to liver damage, intestinal lesions, and hepatic necrosis, which is liver cell death.
All right, so a little bit about fluorescence spectroscopy. First things first, this is a cartoon. So what this guy's doing, he's shining a light into a quartz cuvette, which is what is put into the fluorometer, and then he sees a chemical compound, which is basically what we're doing, except the only difference is that we get a graph output instead of an actual chemical structure. We interpret that graph, which we get a chemical structure, and then we figure out what the chemical is. So when we're doing fluorescence spectroscopy, 6-GP isn't detected using that because it can't do that. And so what we did, we combined 9A, which is 9-chloromethylanthracene, and it has a higher sensitivity in fluorescence. So when it binds together, we can count how much 6-GP, the concentration of 6-GP. The previous method is HPLC, which is high pressure layer chromatography, which has a less sensitive detectability.
And more on that is 9A is a fluorescent molecule, unlike 6-GP. So each time we put it through a fluorescence spectrophotometer, we will detect each of the 9A molecules, and if it is in fact a pure product, when we react 6-GP with 9A, we can in fact see the 9A molecules on smaller concentrations, and what that will mean is that a 6-GP molecule is attached to that, and so that is why we are using 9A.
All right, so these are chemical compounds. First thing is 6-GP, which is right here, which is what we're trying to detect, and that's 9A. So 9A, like Reece said, is fluorescent, so we can use that to detect each other. Ethyl acetate and dichloromethane is one of our solvent systems. It's a 1-to-1 ratio, and we use this for some of our processes. For the other set of processes, we use acetonitrile, which is just the other solvent that we use.
As for our experiment, we have 5 different steps. The first being creating the reaction mixture, the second being thin layer chromatography, otherwise known as TLC, the third being column chromatography, the fourth being nuclear magnetic resonance in an NMR, and the last is fluorescence spectroscopy.
Right over here is S-anthomethyl 6-dipyrene, which is basically the 6-GP and the 9A binding together into acetonitrile, which is just like salt and water. Then we refluxed it. Refluxing is basically when you stick your round bottom flask, which is what we combined everything into, and then we stuck it up a tube. The tube on the outside has cold water running through it, and then the flask is set into a hot water bath. And you can think of this kind of like when you swipe your hand down a cold soda can and all that condensation going down. That's basically what refluxing is.
To use that solvent for later experiments. And so the next step is thin layer chromatography, in which we take a silica TLC plate, as shown above right here, and we use capillary tubes, which collect 1 drop of our reaction mixture. We put 1 drop of our reaction mixture on the right here, as you can see, and 1 drop of 9A standard, and another drop of 6TP standard. And with this, we put it in a developing jar, which contains a 1-to-1 ratio of ethyl acetate and dichloromethane, as seen above. And with this, the capillary action of the 1-to-1 solvent ratio will separate the different compounds within our mixture to find our actual pure product. And above, I list the RS values of each separated compound. We are trying to look for the pure reacted product. And yeah.
All right, the next step is column chromatography, which is basically TLC on a large-scale version. First thing that we did in this column, we took glass wool and we put it down right here so that it would stop the silica, which we're going to add in next, and let the reaction mixture fall through. So next we added 1/5 of the way full of the silica into the column. Then we added a very thin layer of our reaction mixture using a pipette. And then up here in the separatory funnel, we add the 1-to-1 solvent ratio solvent system, and we let it drip right through. And then in these, we had 21 test tubes, and we let it all drip through 1/5 of the way full. And then what we did exactly like we did in TLC, and we added a drop to each one of these, and we figured out if the RF values matched or not. And these 6 dots right here is what we use in our next step.
And the importance of this step is to ensure that these 6 dots are, in fact, our pure product, because without having a pure product, you won't be able to detect the 9A within fluorescence spectroscopy, our next step, to get 6TP, which directly correlates with each other because they are compounded with each other. And our next step is NMR, actually. And so we took an NMR tube and a 9A standard, and we ran it through the NMR as seen here, and it gave us this spectrum. And over here we have the 6TP standard. With this, we also looked at the peaks to decipher which ones matched up with our spectrum, which below is our NMR spectrum when we put the product in the NMR. And the scale, just to note here, the scales of these are not all the same. And in fact, this peak right here, we are trying to look for to disappear to in fact ensure and tell us that it was in fact a pure product and that these two have been fully reacted.
The next step is fluorescence spectroscopy, the main point of this entire project. So the goal was to create dilutions and see which is the smallest solution that we can get to, and then find the limit of detection, which is LOD, and the limit of linearity, which is LOL. So the dilution levels that we started off with are 100 micromolars, and we went all the way down to 10 nanomolars shown right here. First thing we did, we created a blank of acetonitrile because that's the solution that we put it in with, and so it wouldn't detect the acetonitrile into this quartz cuvette right here. If you can see that, it's clear, and that's the fluorometer back there. And we put that in there first, and then we started adding the dilutions after we conditioned the cuvette, which basically means adding a little bit of it, shaking it around, and then getting rid of the solution. And we figured out what our LOD and LOL is.
And if you don't know what NM or that symbol NM is, it means nanomoles and micromoles, as Samyuktha stated. But moles, the molarity of a substance is moles over liters, and moles being, I believe it is it's around 6.23 times 10 to the 23rd molecules in that. As for our results, we found out that using fluorescence spectroscopy, we have a limit of detection of 1 picomolar as compared to HPLC of 20 nanomolars, which is in fact 20,000 times more sensitive. And so that means we can detect it on a much smaller level. And for our limit of linearity, our LOL, is for fluorescence spectroscopy, we have 70 nanomolars as compared to HPLC, which is 5,000 nanomolars. And we put that into ratio to better understand the 71 times better. That is much more sensitive. And below is our graph of the limit of linearity with our R squared value and our linear.
So a perfect R squared value would be 1, but we can't ever get to 1. So we try to get to 0.999, as many 9s as possible, and we got to 0.9953, which is pretty good. So our conclusion, our hypothesis, like we stated beforehand, is that fluorescence spectroscopy is a higher sensitive method in comparison to HPLC, and we supported this by saying that we figured out that the LOD is more sensitive than an HPLC, and the LOL is way better because it was 71 times better.
And if you remember previously, the whole point of this experiment was to detect 6-thiopurine on smaller concentrations due to the severe side effects that it causes within the human body. With these side effects, it is important that we understand chemotherapy and the concentrations in the body so we can limit the severe side effects that it causes for further use. And our limit of linearity will help in further experiments for other scientists to maybe create a better detection method or more time efficient. And I would especially like to thank Cargo Specialty Seeds and Oils, my sponsor, for sponsoring my research, and me to go to this wonderful program.
I'd like to thank Xcel Energy for sponsoring me.
And we would like to thank the FSI staff, Lori Ball, for being a wonderful director.
Chris and Jess for being the best RAs and taking us to Walmart on a daily basis.
And Reece and Amy for being wonderful teachers and counselors whenever we needed.
Sean for being the best mentor and for saying that everything's okay when it's not.
And our families and friends back home.
For supporting us all the way.